Hello to everybody. So I'm happy to be there and to present this. I've been asking to present that because all my colleagues are away on field trips. I'm not really a specialist about black carbon and this kind of processes, but it was really interesting to start documenting myself on that, and I feel it's a good opportunity. Since I'm not really familiar to this, I will be maybe more able to explain it in simple terms. So I hope it helps. So from what I've seen, black carbon is small particles that floating in the air that results from the incomplete combustions of fossil fuels. And the main characteristic of this dust is that it absorbs the solar radiations, which leads to heating of the atmosphere. And when it might be deposited to the snow or to the ice, might lead to more melting. So the question is posed now when we see, so I imagine you have had already a lot of presentation about all this pollution and everything. So we all know, I bet we all know that there is this atmospheric brown cloud above the Indo-Gangetic plain. And we pose the question how that is going to influence the glacier melt and the snow melt and the process related to that. So I put this image to illustrate the density of this dust. So a short summary, I will start to explain a little bit how the dust is impacting on the glaciers. I will have to explain a little bit about the processes of glacier mass balance and the melt process of the snow and the ice. So then I can explain how the black carbon and the dust will affect the cryosphere. And then I will talk a little bit about the state of the knowledge, about the scientific knowledge about all this, about the emissions, the transport of the pollutants, a little bit about the long-term trends that have been measured about the concentration of black carbon, and what do we know about the melt contribution, the contribution to the melt to snow in glaciers. And then I'll talk about a little bit some limiting factors. So how does a glacier work? So this is a sketch of a glacier where we separate the glacier in an accumulation zone and an ablation zone, separated by what we call an equivalent line. What we call the accumulation zone is the place where during the year the surface is accumulating snow, and there's more snow falling than snow melting. So the net balance at the end of the year is that you get more mass of snow and ice accumulated there. That's why it's called the accumulation zone. Then we have an ablation zone where there's not enough snow that falls every year to compensate all the melt during the year. So the line at which there's a separation between the two zones really depends on the height at which you get snow falling, which depends on the temperature. So this is why the glaciers are quite sensible to the temperature, especially because of this snow line. That will be important for the next things. So we are concerned about glacier melting and enhanced melting, because if you have a glacier with a net mass balance, so you have the evolution of the mass balance during time, if this net mass balance is negative, the glacier volume will diminish with time. But this will lead to, first, you will have more melt because you have a negative mass balance, so you will increase the runoff and the water provided by the glacier, which is finally quite a good thing. But with time, with the glacier volume decreasing, you will get a loss of runoff. That's why the melt is concerning. So how does the glacier melt? All the melt is assessed through the energy balance calculation, which helps you to understand all the energy transfer process at the interface between the ice or the snow and the atmosphere. So one of the first elements that is very important in the glacier melt is the solar radiation. Part of the sun, part of the solar energy is incorporated into the snow, but part of it is reflected also. And this reflection part really depends on the reflectivity, which is called the albedo. the reflectivity of the glacier. If you have a big white glacier, it will reflect all the sun and will not melt a lot. If you have a very dark glacier, it will absorb all the radiation and will melt more. There's other terms also that exchange energy with the atmosphere. You have the long wave radiation, which is thermal emission that comes from the atmosphere, from the clouds. It depends on the temperature of the atmosphere. That's where climate change has a big impact, because it acts on the temperature. You have some terms that depends on the precipitation coming inside. And you have also the direct exchange by the flow of the wind above the glacier that exchange direct heat and which depends on the temperature. Then I forgot about all these complicated terms inside. And all this energy inside exchanges just generate the flow of meltwater. So that will help us to understand how the black carbon and the dust will affect the glacier melt or the snow melt. As I said, the black carbon is dark, so when it will deposit on the snow or on the ice, it will cause a reflectivity decrease, will act strongly on the solar radiation that is inputted inside the glacier. But also, not only the black carbon on the snow, but the black carbon in the atmosphere will cause a warming of the atmosphere that can change the long wave radiation or the turbulent energy fluxes, the exchanges with the air directly above the surface. Also, in the literature, you can find, maybe some colleagues will talk about that in further presentations. The precipitation patterns might change because of the black carbon. Black carbon is able to change the precipitation, the way the clouds are forming and the displacements of the clouds. And this might change how the snow is deposited on a glacier, which will act again on the reflectivity. If there's less snow, the glacier will be less reflective and will absorb more solar radiation. And also, there is what we call the climate feedback. It means that if the glacier gets darker, it will get more energy inside, it will get warmer, and that will warm the atmosphere in response. So this is kind of a simple pattern of you put more black carbon, this will melt more the glaciers. Actually, it's not so easy. Let's take a look more inside about all the process. Suppose we start from a dust source, from pollutants in the city, and that black carbon or dust is transported in the atmosphere by different transport processes and is deposited on the snow, on the ice, above in the mountain. This will lead to a darkening of the ice and so more melt because there's more solar radiation absorbed. And so we'll have more melt. This is the simple thing that we know, and it's quite easy to understand. But then you have BC and dust inside the atmosphere, as I told you, which could lead to warmer air. The warmer air leads to enhanced melt from what I showed you before. But warmer air means also that you will have less snow depositing on the glacier because there will be more rain than snow, which means you'll get more darkening. The darkening means that you have more melt. So it starts to be a little bit more complicated. But the darkening means also, because the glacier is warmer, that it will warm the air, so it will enhance the melt. So you have this kind of what we call feedbacks inside. Then the BC and the dust in the atmosphere will impact on the clouds and on the precipitation, as I said. Will that lead to more snow or to less snow? The question is still open. Some people will argue it's less snow or more snow, so we don't know exactly. So it's not a direct pathway from emission of black carbon will lead to this amount of melt compared to without black carbon. It's quite complicated systems. And furthermore, between the urban sources and the snow ice deposition, there's lots of local sources that are quite unknown. They are difficult to assess, like burning forests or burning fires and things like that. So what about the state of the knowledge? What do we know about the sources of black carbon around? If you take different inventories, you will see that, so here you have maps for 2005. The red parts is where you have lots of emissions. The blue parts is where low emissions. And we can see that from different inventories, so different studies, you have quite very different patterns. You always find this lot of emissions there and there, but you see that here you have kind of big differences compared to the other ones, or here also. So even the sources are not well known. Then we can ask, how is the black carbon changing during the season? If you take some measurements, there's only a few places where atmospheric measurements are made in the Himalayas. So here are the points where you have atmospheric measurements. And here are the concentrations that are measured during the summer, monsoon, during the post-monsoon in autumn, during the winter, and during the spring. And this is the mean of everything. So what you see is that in monsoon and post-monsoon, there's not so much black carbon measured in the atmosphere. You find more in the winter and the spring just before the monsoon. And if you take, so this is measurements from atmosphere. If you look now, you can dig inside glaciers. You can dig holes inside the glacier and extract ice cores. And from the layers you see in the ice cores, you can see where the dust is deposited. And when you can date at which time the dust is deposited. So here is an example of a record of black carbon inside an ice core on Mera Peak in the Khumbu Himal. You have the dates here from 2010. This is November to 2000, so it's 10-year records of black carbon. And the peak pikes there just indicate an augmentation in the concentration. And what you see is that it's always in between the summers. The resolution is not so nice, but you have more concentration of black carbon between the monsoons. So the atmospheric measurements quite agree with the ice measurements. How can we explain this pattern of monsoon deposition, monsoon no deposition and more deposition just before the monsoon? So you have to understand a little bit how the circulation is around the Himalayas. So that's here. In the winter, you have more predominant westerlies, so big winds coming from the west that drive all the pollution in the Ganges up to the mountains. So that's why you find more black carbon deposition during the winter. During the monsoon, you have these winds coming more from the Gulf of Bengal, but due to precipitation, the precipitation just makes the air clearer. You know that in the monsoon in Kathmandu, for example, you have much more clear air than in general. So you have much less deposition at this moment. So the deposition from the source to the mountains depends on this large-scale circulation, but also on the local convection, which is generated by the sun on the mountains that brings the air during the day from down the valley up to the valley. And this more has to do with the local sources. And all these patterns of big circulation and local circulation just lead to complex fine-scale processes that are not easily modeled now for the moment. So there's a lot of uncertainties on how the transport process from the urban cities to the glacier are done. So here's an example of black carbon records from ice cores at different places in the Himalayas. So you can see that this is to pose the question of about the long-term trends. Is the black carbon concentration begin to be higher in the ice or in the snow? So what you see is that there's a lot of variability. And from the yellow curve, the green curve, or the pink curve, you see like a little bit of augmentation in the last years. But the tendency is not so clear. Finally, what is exactly the impact on melt of the deposition of black carbon on glaciers? So we have a colleague from France that did a study on still the Mera Peak using the same ice core that I showed before, that showed that in 10 years, the black carbon deposition could account for about 26% of the total melt that is observed. So that is not negligible. It's not neither the main contribution to the melt. Where you can see the snow in the glaciers and some debris-covered glaciers, some black things that might be. Actually, I'm a bit prudent about this because this could be just debris covering the glacier. so it might not be dust deposited by storms. And this could be also bare ice. Just to show you that there's some limiting factor in the knowledge that we have. Like important parts of the Himalayas, in the glaciers in the Himalayas, are covered by debris. So this is an example of the Langtang Glacier where you have this huge amount of debris above the ice. So deposition of dust in such kind of glacier wouldn't have any impact on the melt of this glacier. It doesn't change anything. You have one meter of debris, you just add some thin layer of dust, it doesn't change anything. Here I put a photo of the Yala Glacier as I observed it in September, where you see that you have this ice appearing there, which is quite dirty, actually. This is the natural state of the ice when the snow is removed. Also, if you deposit black carbon on the snow parts, you may have a great impact on the melt, but if you deposit it on the ice, it won't change anything. And okay. So I question the impact of black carbon at some places because there is important debris covered. The impact on bare ice is not so relevant. And there might be also natural source of dust, like wind transporting dust from the valleys, etc. So I just gave you a quick overview, some take-home message. So we might have an increasing anthropogenic black carbon and dust emissions, and this might lead to increased snow and glacier melt. But there are complex feedbacks, like I showed you this diagram with the arrows everywhere. And the exact processes of the transport, the deposition, and how it affects the melt are not totally well understood yet. And we really lack in situ measurements. Thank you for your attention.
Thank you.
Thank you.